Hello, in this lecture we find out the area of the green shape. In the drawing we have a circle. Inside this quarter circle, we know that the radius of this small circle equals to the square root of 2 units in its length. Our mission is to find out the area of this green shape. So first of all we define the points that are relevant to this question. We define this point as O. We define this point as B. This is the center of the quarter circle. We define this point as O. We define this point as C. We define this point as D. This is the touching point of this small circle with this quarter circle. We define the touching point is E. And finally, we define the center of this small circle, this point, as F. In the next step, we will join points F and C together by a straight line. Point F is the center of this small circle, point C is the point on the small circle itself, therefore FC is the radius of this circle. That is equals to the square root of 2 units according to what is given in the question. You can implement here rule 1 and I'll click quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In this drawing we have a circle and we have tangent AB. This is tangent AB, that is tangent to this circle at this point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. We can actually implement this rule in our drawing. Why? Because in our drawing we have the radius FC of this small circle that is drawn to point C, that is the point of tendency of tangent OD with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 1. We have the radius FB of this small circle that is drawn to point B, that is the point of tendency of tangent AD with this circle, with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius BF. If AD is perpendicular to BF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule 1. In the next step we focus on this small quadrilateral BFOC. Inside this small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here, the missing fourth angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside quadrilateral BFOC to 360 degrees, the size of this angle must be equal to 90 degrees. So inside quadrilateral BFOC we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral BFOC is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle BFOC, side BF must be equal to the opposite side OC. But BF equals to the square root of 2, therefore OC, the opposite side OC, must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, the side BO must be equal to the opposite side FC in rectangle BFCO. But FC equals to the square root of 2 units, therefore the opposite side BO must be also equal to the square root of 2 units in its length. So actually found out that quadrilateral BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this square is equal to the square root of 2 units in its length. In the next step, we will join points O and F together by a straight line. And we will focus on this small right triangle, triangle OBF. In this small right triangle OBF, those two sides they are both equal to the square root of 2, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be equal to each other. So if we define the size of this angle as alpha, then the size of the other angle must be also equal to alpha because they are equal to each other. The sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the right triangle OBF. So which angles we have inside the right triangle OBF? We have this angle is equal to 90 degrees. It is a right angle plus alpha, that is 2 alpha. In total, they must be equal to 180 degrees. Repeat again. In the right triangle OBF, (90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract 90 degrees from this equation. And you get that 2 alpha equals to 180 degrees minus 90 degrees is equals to 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2. And finally we get that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. So actually, this is angle alpha is equals to 45 degrees in its size. And this is also angle alpha that is equals to 45 degrees in its size. We will continue to focus on the right triangle OBF. Here we'll implement the Pythagoras theorem on this right triangle OBF. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle OBF, OF square, the hypotenuse is OF, therefore the square of the hypotenuse is OF square, must be equal to OB square plus BF square. Repeat again, in the right triangle OBF, OF square equals to OB square plus BF square, so OF square, that is the square of the hypotenuse, equals to OB square. OB is square root of 2, therefore OB square is square root of 2 square, that is 2, plus BF square. BF is also square root of 2, therefore BF square is square root of 2 square, that is 2. So in conclusion, we found out that OF square equals to 2 plus 2, that is 4. So OF square equals to 4. Here we take a root out of this equation, and finally we get that OF equals to the square root of 4, that is 2. So here, the length of line segment OF is equals to 2 units. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 9. According to rule 9, if two circles touch each other internally, here in the drawing we have the big circle touches this small circle internally at point P. Because of the fact that the small circle is located inside the big circle, therefore they are touching each other internally at point P. So whenever you have an internal notch between two circles, like in this drawing, then the straight line that connects their centers together must pass through their touching point. The center of this big circle is here at point O, the center of this small circle is here at point M, and the straight line that connects their centers together is the straight line OM. So the straight line OM must pass through their touching point. Their touching point is P. So the straight line OM must pass through point P. That is to say, OMP is one straight line. Again, OMP is one straight line. So whenever you have an internal notch between two circles, then the straight line that connects their centers together must pass through their touching point. Like here, the straight line OM must pass through point P, or OMP is one straight line. We can actually implement rule 9 in our drawing. Why? Because in our drawing we have the small circle is located inside the quarter circle, therefore we have here an internal notch. The small circle touches the big semicircle at point E. And because of the fact that the small circle is located inside the big quarter circle, we have here an internal notch between those two circles and this quarter circle. Therefore, for that reason, we can implement here rule 9 because we have here an internal notch. That is to say, the small circle touches internally the big semicircle at point E. So we can implement here rule 9. The center of the big quarter circle is here at point O. The center of this small circle is here at point F, and the straight line that connects the centers together is the straight line OF. And according to rule 9, the straight line OF that connects their center together must pass through their touching point. Their touching point is here. So the straight line OF must pass through point E. Or OFE is one straight line. Again, OFE is one straight line according to rule 9. OFE is one straight line. Okay, so OFE is one straight line. If OFE is one straight line, it means that OE is also a straight line. OE is a straight line, but what is the definition of the straight line OE? Point O is the center of the quarter circle. Point E is the point of the quarter circle itself. Therefore, line segment OE is the radius of this quarter circle. We define the radius of this quarter circle as capital R. So capital R equals to OE. What is the length of OE? From the drawing, it is very easy to see that OE in total equals to OF plus FE. Again, OE equals to OF plus FE. OE equals to OF plus FE. What is the length of line segment FE? Point F is the center of the small circle. Point E is the point on the small circle itself. This is exactly the definition of a radius. That is to say, FE is the radius of this small circle that is equal to the square root of 2 units in its length. So OE equals to OF, that is 2, plus FE, that is square root of 2. In conclusion, we found out that capital R, that is the radius of this quarter circle, equals to 2 plus square root of 2. Capital R equals to 2 plus square root of 2 units in its length. Okay. Here we define the point of tendency of tangent OE with this small circle as H. The straight line edge E is part of the radius OE, therefore it is absolutely a straight line. Again, line segment edge E is part of the radius OE, that is a straight line, therefore line segment edge E must be also a straight line. So edge E is a straight line. Edge E is a straight line that touches the small circle here at point H and here at point E. And any straight line that touches the circle at 2 points must be a chord. So edge E is a chord inside the small circle. Edge E is a chord that passes through point F, that is the center of the small circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, edge E is the diameter of this circle. Edge E is the diameter of the small circle. If edge E is the diameter of the small circle, we know that the diameter of any circle bisects the circle into 2 halves. So edge E bisects this small circle into 2 halves. This is the first half and this is the second half. Half of any circle it is a semicircle. Therefore, this is a semicircle. So this is a semicircle of the small circle. This is half of the size of this small circle. Okay. In the next step, I will present to you what is a sector. Here, this green shape edge OB is a sector. A sector is part of a circle. So AOB is a sector. AOB, a sector is like a slice of a cake. If the cake is the circle, then a sector is a slice of a cake. So AOB is a sector. The sector AOB consists of two legs, leg AO and leg BO. Both those two legs of this sector are the radii of this circle that is equal to R. Okay? And the angle between those two legs is theta. So the area of this grand sector AOB equals to pi r squared, that is the area of this circle, times theta over 360 degrees. Again, theta is the angle between the legs of this grand sector AOB. Repeat again that the area of this sector equals to pi r squared times theta over 360 degrees. Our mission is to find out the area of this green shape. So, what is the area of this green shape? The area of the green shape from the drawing, it is very easy to see that the area of this green shape equals to the area of sector AOE here. This is how I write down the area of a sector. This sign above AOE is the sign for a sector. It means the area of sector AOE. So the area of the green shape equals to the area of sector AOE minus the area of the semicircle minus the area of the small semicircle minus the area of this shape HBO. Again, minus the area of the orange shape HBO. Repeat again, the area of this green shape equals to the area of the big sector AOE minus the area of this semicircle minus the area of this orange shape HBO. Yeah. The area of the green shape in total, it is equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. So we have to find out the area of sector, the big sector AOE. The area of this big sector AOE. What is the area of the big sector AOE? The area of any sector equals to the area of the circle that contains the sector. Here, sector AOE is part of the big circle. So the area of the big circle equals to pi times capital R squared. That is the area of the big circle times theta over 360 degrees. Theta is the angle between the legs of this sector AOE. The angle between the legs of this sector AOE is this angle, and this angle equals to 45 degrees according to what we have already found out. So it is 45 degrees over 360 degrees. So in conclusion, we found out that the area of the big sector AOE equals to pi times capital R squared, that is the area of the big circles, times 45 degrees over 360 degrees. 45 degrees is the area between the legs of sector AOE. So the area of sector the big sector AO equals to pi times r squared. And we have already found out that times capital R squared. And we have already found out that capital R equals to 2 plus square root of 2. If capital R equals to 2 plus square root of 2, it means that capital R squared equals to 2 plus square root of 2 squared. So in total, the area of the big circle pi r squared equals to pi times 2 plus square root of 2 squared times 45 degrees over 360 degrees. 45 degrees over 360 degrees equals to 1 over 8, so we have to divide the area of the big circle by 8. So the area of sector AOE, the big sector AOE equals to pi times 2 plus square root of 2 squared. 2 plus 2 plus square root of 2 squared equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times 2 times square root of 2 squared, according to the algebraic identity, that a plus b squared equals to a squared plus b squared plus 2 times ab. And we have to divide it by 8. So the area of the big sector AOE equals to pi. Inside the brackets we have 4 plus 2 is 6, plus 2 times 2 is 4. So in total this expression equals to 4 times square root of 2 divided by 8. Here we divide both the numerator and the denominator of this expression by 2. And we will get that the area of the big sector AOE in total, it will be equal to pi, inside the brackets we have 6, and 6 over 2 is 3, plus 4 times square root of 2. 4 times square root of 2 over 2 is 2 times square root of 2, and we have to divide it by, we have in the denominator 8, and 8 over 2 is 4, because we divided both the numerator and the denominator of this expression by 2. So in conclusion, we found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we'll find out the area of the small semicircle. The area of this small semicircle. I remind you that the area of the green shape in total equals to the area of sector AOE minus the area of this small semicircle minus the area of this orange shape BHO. So in the next step we find out the area of this small semicircle. What is the area of the small semicircle? The small semicircle is part of this small circle. And we know that the radius of this small circle is r. Therefore, the area of the semicircle will be equal to pi r squared, that is the area of the small circle, over 2. It is given us the question that r, that is the radius of this small circle, equals to the square root of 2 units in its length. If r equals to the square root of 2, it means that r squared equals to the square root of 2 squared, that is 2, divided by 2. 2 over 2 is 1, so we left here with pi. In conclusion, found out that the area of the small semicircle is equal to pi square units. And finally, we have to find out also the area of this orange shape BHO. What is the area of the orange shape BHO? the drawing, it is very easy to see that the area of this orange shape equals to the area of triangle FOB minus the area of this small sector FBH. The area of this small sector FBH. That is part of the small circle. So minus the area of the small sector FBH. Repeat again. The area of the orange small sector BHO equals to the area of the right triangle FOB minus the area of the small sector FVH. So the area of the orange shape BHO in total is equals to the area of triangle FOB. The area of any triangle equals to the base of the triangle times the height to the base over 2. In this right triangle FOB, the height equals to the base, they are both equal to the square root of 2 units. So the base is square root of 2 times the height that is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion, we found out that the area of the right triangle FOB equals to 1 square units, and we have to subtract from the area of the right triangle FOB the area of the small sector FBH. What is the area of the small sector FBH? The area of this small sector FBH. The area of the small sector FBH will be equal to the area of the circle that contains the sector. That is actually the area of the small circle, that is pi r square, times the angle between the legs of this small sector. The angle between the legs of this small sector is 45 degrees. So it is 45 degrees over 360 degrees. So pi r square is pi and r is square root of 2, therefore r square is square root of 2 square. Square root of 2 square is 2. And 45 degrees over 360 degrees, it is 1 over 8, so we have to divide this expression by 8. Here we divide both the numerator and the denominator of this expression by 2. In the numerator we have 2 pi over 2 is pi, in the denominator we have 8 over 2 is 4. So in conclusion, we found out that the area of the small sector FBH equals to pi over 4. Therefore, in total, the area of the orange shape BHO will be equal to the area of triangle FOB, that is 1 square units, minus the area of the small sector FBH, that is pi over 4. So it is 1 minus pi over 4 square units. And again, the area of the orange shape BHO equals to 1 minus 4 over pi square units. So the area of this green shape is equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape BHO. repeat again. The area of the green shape in total equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So the area of the green shape in total will be equal to the area of the big sector AOE. We already found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the small semicircle, that equals to pi square units minus the area of the orange shape BHO, that is equals to 1 minus pi over 4 square units. So the area of the green shape in total equals to the value of this expression. So here we'll open the brackets and we get that the area of the green shape in total will be equal to pi times 3 plus 2 times square root of 2 over 4 minus pi. Here we have, we'll open the brackets here, we'll have here minus 1, and we have minus times minus is plus, so it is minus 1 plus pi over 4. So the area of the green shape in total will be equal to here pi, inside the brackets we have 3 plus 2 times square root of 2 over 4, and here we have minus pi plus pi over 4, it is equals to minus 3 quarters pi minus 1. Here we multiply minus 1 by 4 and then we divide it by 4 in order to a common factor with the other two expressions. So minus 1 times 4 is minus 4 divided by 4. So the area of the green shape in total equals to, here we'll open the brackets, pi times 3 is 3 pi, and 2 times 2 times pi is 2 times square root of 2 times pi is 2 times square root of 2 times pi, and divided by 4 minus 3 pi minus 4. So here we have 3 pi minus 3 pi is 0, so 3 pi will get cancelled, and we left only with 2 times square root of 2 pi minus 4 over 4. So here we divide both the numerator and the denominator of this expression by 2, and we get that 2 times square root of 2 times pi over 2 is square root of 2 times pi, and minus 4 over 2 is minus 2, and we have to divide the denominator of this expression by 2 also, because we divided both the numerator and the denominator of this expression by 2. So 4 over 2 is 2. So in conclusion, we found out that the area of the green shape in total equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, it is equals to 1.2214 square units. So I'll repeat again. The area of this green shape equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape equals to 1.2214 square units. Okay, so in the next step I will summarize the lecture. In this lecture we found out the area of this green shape. In the drawing we have a circle inside this quarter circle. We also know that the radius of this small circle r equals to the square root of 2 units in its length, and our mission is to find out the area of this green shape. So first of all, we defined the relevant points in this drawing, the relevant points to the answer to the question in this drawing. We define this point as A, we define this point as B, we define this point is the center of the quarter circle. So we define the center of the quarter circle as O. We define this point as C, we define this point as D. This point is the touching point between the small circle and the big quarter circle. We define the touching point as E. Or we can say that is the point of tendency of this small circle with this big quarter circle. And finally, we defined the center of this small circle as F. This point is F. Then we join points F and C together by a straight line. What is the definition of line segment FC? Point F is the center of the small circle, point C is the point on the small circle itself, therefore FC is the radius of this small circle that is equals to the square root of 2 units in its length, according to what is given as the question. Here the radius FC is drawn to point C, that is the point of tendency of tangent OD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius FB of the small circle that is equals to the square root of 2 units in its length. The radius FB is drawn to point B, that is the point of tendency of tangent AD with the small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius BF. If AD is perpendicular to BF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. Inside the small quadrilateral BFOC, inside the small quadrilateral, we have 1, 2, 3 right angles. The sum of right angles is 270 degrees, plus the size of this fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside this small quadrilateral BFOC to 360 degrees, the missing angle here must be equal to 90 degrees in its size. So inside the small quadrilateral BFOC, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this small quadrilateral BFOC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF must be equal to the opposite side OC. In rectangle BFOC. So BF equals to OC, but BF equals to the square root of 2. Therefore OC must be also equal to the square root of 2 in its length. Likewise, according to the same rule, side FC must be equal to the opposite side BO in rectangle FBOC. But FC equals to the square root of 2, therefore BO must be equal to the square root of 2 units in its length. So we found out that quadrilateral BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this square equals to the square root of 2 units in its length. In the next step, we join points F and O together by a straight line. By joining points F and O, we created the right triangle FBO. In the right triangle FBO, those two sides they are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also note that the sum of the angles in any triangle it is equal to 180 degrees. And especially it is true in the right triangle FVO. The sum of the angles must be equal to 180 degrees. So which angles we have? We have this angle alpha, the other angle that is alpha plus alpha is 2 alpha, plus this angle that is 90 degrees. In total it must be equal to 180 degrees according to the rule that I mentioned. So 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract 90 degrees from this equation and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. Here we divided this equation by 2 and finally found out that the missing angle alpha equals to 45 degrees in its size. So this is angle alpha that is equal to 45 degrees and this is also angle alpha that is equal to 45 degrees in its size. We continue to focus on this right triangle BOF and we implemented the Pythagoras theorem in the right triangle BOF. According to the Pythagoras theorem in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle BOF is OF, therefore the square of the hypotenuse is OF square, and it must be equal to BF square plus BO square. Repeat again, in the right triangle BOF, according to the Pythagoras theorem, OF square must be equal to OB square plus BF square. So OF square, that is the square of the hypotenuse, must be equal to OB square. OB is square root of 2, therefore OB square is square root of 2 square, that is 2, plus BF square. BF equals to the square root of 2, therefore BF square is the square root of 2 square, that is 2. So in conclusion, we found out that OF square equals to 2 plus 2, that is 4. Here we took a root from this equation and finally found out that OF equals to the square root of 4, that is 2. So the length of the hypotenuse OF, it is equal to 2 units. Then I presented to you rule 9 and we presented rule 9 in our drawing. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. In the drawing we have those two circles. The small circle is inside the big circle. Therefore, we have here an internal notch between those two circles. That is to say, they are touching each other internally at point P. Point P is their touching point. The center of the big circle is here at point O, and the center of this small circle is here at point M. And the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM that connects their centers together must pass through their touching point, that is actually point P. OM must pass through point P. Or OMP is one straight line. Again, OMP is one straight line. So whenever you have an internal notch between two circles, you can implement rule 9. That is to say, whenever we have two circles that touch each other internally, you can implement rule 9. Actually, we can implement rule 9 in our drawing. Why? Because in our drawing we have an internal notch between this small circle and the quarter circle. That is to say, the small circle touches the big quarter circle here at point E. And because of the fact that the small circle is located inside the big quarter circle, there is an internal notch between those two circles. For that reason, you can implement here rule 9. According to rule 9, here the center of the big quarter circle is here at point O, the center of this small circle is here at point F. And the straight line that connects their centers together is the straight line OF. And according to rule 9, the straight line OF must pass through point E, that is their touching point. Or OFE is one straight line. OFE is one straight line according to rule 9. OFE, what is the definition of line segment OFE? That is a straight line. OFE is also the radius of this quarter circle. Why? Because point O is the center of the quarter circle. Point E is the point of the quarter circle itself. This is exactly the definition of a radius. Therefore, OFE is the radius of the quarter circle. We define the radius of the quarter circle as capital R. Therefore, OFE equals to capital R, or OFE is OE. This is equal to capital R. So what is the length of capital R? That is the radius of the quarter circle. Capital R is equal to OFE equals to OF plus FE. Capital R equals to OF plus FE. OF is 2 and FE is square root of 2, because it is the radius of the small circle. So in total, capital R equals to 2 plus square root of 2. Okay, the radius of the big circle, capital R equals to 2 plus square root of 2. And we found out that OE is the radius of the big circle. If OE is the radius of the big circle and edge E is part of the radius, therefore it also must be a straight line. So edge E is a straight line. Edge E is the straight line that touches the circle, the small circle is here at point H and here at point E. Therefore, edge E is a straight line. Whenever you have a straight line that touches the circle at 2 points, it must be a chord. So edge E is a chord inside this small circle. It is a chord that touches. It is a chord that passes through point F. That is the center of this small circle. And any chord that passes through the center of a circle must be the diameter of a circle. Therefore, edge FE is the diameter of the circle. If edge FE is the diameter of the circle, it means that edge E is also the diameter of the circle. So edge E is the diameter of the circle. And you know that the diameter of any circle bisects the circle into 2 halves. Here edge E bisects this small circle into 2 halves. This is the first half and this is the second half. Therefore, this is a semicircle. A semicircle is half of the circle. So in conclusion, we found out that this shape is a semicircle. Okay. In the next step, I presented to you what is a sector. Here, the green shape here, A or B, is a sector. A sector is a part of a circle. A sector is like a slice of a cake. If the circle is a cake, then a sector is a slice of a cake. It is a part of the circle. So A or B is a part of a circle. The sector A or B consists of 2 legs. The first leg is AO and the second leg is BO. Both legs are the radii of this circle that is equal to R. And the angle between the legs of this sector A or B is theta. So the area of this sector equals to the area of this circle that is pi r square times theta over 360 degrees. Again, theta is the angle between the legs of this sector. Again, the area of any circle equals to the area of the circle that contains the sector. Here it is pi r square times the angle between the legs of the sector, that is theta over 360 degrees. Okay, so the area of any sector equals to the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. Again, our mission is to find out the area of this green shape. What is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of sector AOE the area of this big sector AOE, minus the area of this small semicircle, minus the area of this orange shape BHO. Again, the area of the orange shape equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape BHO. Repeat again, the area of the green shape in total it is equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. So what is the area of the big sector AOE? The big sector AOE is a part of the big circle, and the radius of the big circle equals to capital R. Therefore, the area of the big circle must be equal to pi times capital R squared. Therefore, the area of the big sector AOE that is part of the big circle must be equal to the area of the big circle that is pi R squared times the angle between the legs of this sector. Those are the two legs, and the angle between the two legs is equal to 45 degrees. So it is 45 degrees over 360 degrees. So the area of sector AOE equals to pi R squared. R equals to 2 plus square root of 2, therefore R squared equals to 2 plus square root of 2 squared. So in total, the area of the big circle equals to pi times 2 plus square root of 2 squared times 45 degrees over 360 degrees. 45 degrees over 360 degrees is 1 over 8, so we have to divide the area by 8. So what is the value of this expression? It is equals to pi, and 2 plus square root of 2 squared according to the algebraic identity that a plus b squared equals to a squared plus b squared plus 2 times ab. 2 plus square root of 2 squared will be equal to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2 squared, all divided by 8. So we have the area of the big sector AOE equals to pi. Inside the brackets we have 4 plus 2, that is 6, and 2 times 2 is 4. So in total, this expression in the numerator will be equal to 4 times square root of 2 divided by 8. Here we divided this expression, both the numerator and the denominator of this expression, by 2. So we have here pi, and inside the brackets we have 6. 6 over 2 is 3. And we have 4 times square root of 2. 4 times square root of 2 over 2 is 2 times square root of 2. So in total, in the numerator of this expression after we divide it by 2, we will have pi times 3 plus 2 times square root of 2, and we have to divide the denominator 8 by 2. 8 over 2 is 4. So here we have 4. So in total, the area of the green sector AOE equals to pi times 3 plus 2 times square root of 2 over 4. In the next step, we have to find out the area of the small semicircle. The area of this small semicircle. The semicircle is part of this small circle, and the radius of the small circle equals to R. So the area of the semicircle will be equal to pi R squared, that is the area of the circle, divided by 2. It is given us the equation that the radius of the small semicircle R equals to the radius of the small circle R equals to the square root of 2. If R equals to the square root of 2, it means that R squared equals to the square root of 2 squared, that is 2, divided by 2. So in total, the area of the small semicircle equals to 2 pi over 2. 2 over 2 is 1, so we left only with pi. When we found out that the area of the semicircle equals to pi square units. The area of this small semicircle equals to pi square units, and we have to subtract also here the area of this orange shape HBO. Okay, the area of this orange shape HBO. What is the area of the orange shape HBO? From the drawing, it is very easy to see that the area of this orange shape HBO, it will be equal to the area of triangle FOB minus the area of the small sector FBH. Again, the area of the big this triangle FBO minus the area of this small sector FBH will be equal to the area of the orange shape HBO. Repeat again, the area of the orange shape BHO equals to the area of the right triangle FOB minus the area of the small sector FBH. So it is equals to the area of triangle FOB, and the area of any triangle equals to the base of the triangle times the height to the base over 2. Here, the base of this triangle is square root of 2, and the height is also square root of 2. So the base is square root of 2, and the height is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So in conclusion, we found out the area of this right triangle FBO equals to 1 square units, and we have to subtract also the area of this small sector FBH. The small sector FBH is part of the small circle, so the area of the sector will be equal to the area of the sector to the area of the small circle, that is pi r square, times the angle between the legs of this small circle, that is 45 degrees over 360 degrees. So in total, the area of the small sector FBH will be equal to pi r square times 45 degrees over 360 degrees. R equals to square root of 2, it is the radius of the small circle, therefore r squared is square root of 2 squared, it is 2. So in total, the area of the small circle will be equal to 2 pi, and 45 degrees over 360 degrees, it is 1 over 8. So it is 2 pi over 8. Here we divided both the numerator and the denominator of this expression by 2. So 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that the area of the small sector FBH is equals to pi over 4. In total, the area of the orange shape BHO equals to the area of the right triangle FOB, that is 1, minus the area of the small sector FBH, that is pi over 4. So it is in total equals to y minus pi over 4. Again, the area of the orange shape in total equals to 1 minus pi over 4. And the area of this green shape in total, it is equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape VHO. Repeat again, the area of the green shape in total equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the small orange shape VHO. We have already found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 minus the area of the semicircle, that is pi, minus the area of the orange shape BHO, that is 1 minus pi over 4 square units. So in total, this expression is the value of the green shape. It is the size of the green shape. So what is the value of this expression? Here we have pi times 3 plus 2 times square root of 2 over 4 minus pi. We open the brackets here. After we open the brackets, we will have minus 1, and minus 1 times minus 1 is plus, so it is plus pi over 4. So in total, we will have minus 1 plus pi over 4. So the area of the green shape in total will be equal to pi times 3 plus 2 times square root of 2 over 4. And here we have minus pi plus pi over 4 is minus 3/4 pi minus 1. Here we multiply minus 1 by 4 and we divide it by 4 in order to overcome a factor with the other two expressions. So minus 1 times 4 is minus 4 divided by 4. And we open the brackets of this expression here. Pi times 3 is 3 pi, and pi times 2 times square root of 2 is pi times square root of 2 times 2. Minus 3 pi minus 4. 3 pi minus 3 pi is 0. After we cancel 3 pi, we left only with 2 times square root of 2 pi minus 4 divided by 4. Here we divided both the numerator and the denominator of this expression by 2. So here 2 times square root of 2 pi over 2 is square root of 2 times pi, and minus 4 over 2 is minus 2, and we have to divide the denominator of 4 by 2, so 4 over 2 is 2. So in total the area of this green shape is equal to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape is equal to 1.2214 square units. Okay, thank you very much.